So in section 1.2, we're constructing models to solve problems. And much of what you're going to be doing here at the beginning is, you don't have to write it down because it's already on the sheet that it gave you. And we're going to just chat through it. So models is what we're doing in this section. A formula is an equation involving two or more variables. A function is a rule for determining the value of one of the variables from the value of one or more variables. And there are some common formulas that you have seen, some of them before, some of them may be less common than others, but different ones of them we'll need today and into your homework. Simple interest is I equals PRT. So jotting these things down to the side, I'll say them out loud and you can write them. I is interest. Okay, so that's how much money you make on your money. P is principal. Principal is the amount of money you put into an investment. R is your interest rate as a decimal. So, for example, if the interest rate's 4%, you have to change 4% into a decimal, which is 0.04. And then T is time, and time's always in years. Time in years always. Later on, I can't remember in which chapter, we'll see another interest formula, but for now, simple interest is the one we're going to work with. Perimeter. The perimeter of a rectangle specifically perimeter is the distance around something, if you'll remember. L is for the length and W is for the width. So 2 times the length plus 2 times the width. That one should be very familiar to you. That's like middle school. Distance. You can find the distance by multiplying the rate. That's how fast something's going, times the time, how long it's going for. That time doesn't necessarily need to be in years. In fact, it usually isn't. It's in whatever measurement is going on. So it could be in seconds or it could be in minutes. It could be in hours, those kinds of things. Your temperature. So this is an equation that converts Fahrenheit to Celsius. And if you use it the other direction, you can convert Celsius to Fahrenheit. So we take our 5/9 times the Fahrenheit minus the 32 degrees. Sales tax. If you've ever bought anything, you've got sales tax on it in Oklahoma anyway. It's not true in every state, but it is in Oklahoma. So sales tax is the price of the product plus the rate, right, the tax rate. I can't remember what it is in Shawnee right now, but it's getting close to 10%, times the price, and then you add those together. So it's showing up on the receipt at the bottom as the sales tax, amount, and then adds it into the price of whatever you purchased before that. The area of the rectangle is the length times width. And then the last one may be a new one that you've not seen, or at least haven't seen used frequently, and it's work. So work is, again, rate times time. So it's a lot like distance. It's just calculating not the amount of distance something traveled, but the amount of work that was done in a particular situation. But the formula is actually the same. So what we're going to be doing in this lesson, there's a few at the beginning where we're just simply moving variables around and learning how to solve for things. But as we continue on, we're going to encounter some word problems. We're going to be setting up formulas. And after we set them up, we're going to be solving for different quantities. So to start with, we are just manipulating equations. So in this, there's actually nothing different than what happened in section 1.1. But it feels different because there's not a whole bunch of numbers involved. And at the end, I'm not going to get A equals a number or whatever, all right? I'm going to get variables on both sides. There's still going to be variables everywhere. So as we're taking a look at the first one on part A, does anybody know what that equation is? A equals 1/2 BH?
The area of a triangle.
Right, good. It's the area of a triangle. So this is an area of a triangle formula. There's at least a couple of different ways you could approach solving this for the letter B. I have a 1/2 in here, so technically you could divide the 1/2 to the other side, but we talked about in chapter P the fact that we can actually multiply by reciprocals as well. Do y'all remember doing that? So that's actually the way that I tend to think about this, is multiplying by reciprocals. So I'm going to just deal with the 2 for now. So if I multiply both sides by 2, then I'll have 2A equals BH, because 2 times 1/2 is 1, right? Or 2 over 1 times 1/2 is 1. And then what would I need to do to solve for b, right, to get b all by itself? Yeah, I would need to divide by the h. So I've got b on one side, and I have 2a over h on the other side, or if it bothers you, you can rewrite it with the b on the left and 2a over h on the right. It doesn't make any difference. But that would be the equation solved for b. So there's nothing different. I'm just multiplying and dividing, just like I would have if there were numbers involved, just there simply aren't numbers involved in the place of the a and the h in this case. Next one, b, is ax plus by equals c. And it wants us to solve it for x. So when we're solving equations, it's sort of the opposite of order of operations. Order of operations, we work from the inside out. And when we're solving equations, we work from the outside in to isolate whatever variable we're working with. So looking at this one, we have an x here. And so we want to move the things that are furthest away from x first. And what is furthest away from x is the by. And how is the by attached? What operation attaches it to the x? Addition, right? So this is the addition operation that we have to undo, which means how am I going to move the by to the other side? Subtraction. So I'm going to subtract, hang on, try one more time. Okay, I promise I'm trying to cut it. All right, I'm going to subtract the by from both sides. So I'm going to have ax on the left and c minus by on the right. Okay, so we're sort of halfway there. I'm trying to isolate x. So right now the x is being attached, or it has attached to it the a. How are the a and the x attached? What operation? Multiplication. So in order to undo multiplication, I need to use division. I need to divide. So I'll divide both sides by a. So x is equal to c minus by over a. Again, there's no numbers to put in for the c, the b, the y, the a, and all of that, but this is solved for x, which is what I was asked to do. Any questions on that one? Okay, number 3 is definitely the messiest looking one, because I have a bunch of fractions, right? So my goal is to solve for R2, which is right here, and it's in the denominator as well, which makes it messier. So as I'm solving for this, again, there's options. I have lots of ways that I could approach this problem. One option is that you could try to just get rid of all the denominators. Okay, that's one option. The other option is that you could try to get the 1 over the R2, the 1 over the R2 by itself first, just by shifting things around with addition and subtraction. I think that's probably the easiest on this particular one. Other ways will work too, but would you like to give that one a try? Okay. So the 1 over the R1 and the 1 over the R3, they're added to the 1 over R2, right? So just like on the previous problem, if they're added, I want to undo it with subtraction. So I'm going to shift them to the other side of the equation with subtraction. So I'm going to subtract the 1 over R1 and the 1 over R3. So minus 1 over R1 minus 1 over R3. So on the left-hand side, I have 1 over R minus 1 over R1 minus 1 over R3. And it equals 1 over R2. Now, it would be so amazingly wonderful if we could just flip them all upside down. We absolutely cannot do that. That will not give us the right value. Okay? So we have to deal with it in a different way. And what we need to do is, we do want to flip them upside down, let me clarify. That is definitely what we want to do. But the reason it won't work is because on the right-hand side, the left-hand side from where you are, the left-hand side, there's separate fractions. It's not one massive fraction. If I had one fraction on the left, I could flip these dudes both upside down and we'd be good to go and all done. But I don't have just one fraction on the left. I have 3 fractions. So I need to take those 3 fractions and merge them into one fraction. And how do I add and subtract fractions from each other? What do I need? Common denominators. Right, they got all match. So in order to get a common denominator here, I need to multiply the denominators by the pieces that they don't currently contain. For example, on the first one, it needs to be multiplied by R1. Hang on. And R3. And if you do it to the numerator, the denominator, you need to do it to the numerator. I think I need to spread this out a little bit, so I'm going to give myself a little bit more room to work. On the second one, it needs to be multiplied by R, because it doesn't have an R, and by R3, because it doesn't have an R3. And on the third one, it needs to be multiplied by R and R1. Does that make sense to everybody? All the pieces that are not currently a part of the denominator in each individual case have to be multiplied by the denominator. So my denominator will end up being R1, R3, and R, right? R1, R3, and R. So in the numerator now, I have R1, R3, and then there's the subtraction sign that occurs between the first two fractions. The second numerator is R, R3, and then there's another subtraction sign. And then the third numerator is R, R1. And then the denominator that matches across all three of them is R, R1, R3, in whatever order you like. It doesn't matter what order that denominator is, but it'll have those three components. And the right-hand side, which I didn't manipulate at all, is 1 over R2. So once I get them to have one fraction on both sides, I can flip both of them upside down. Okay? So you might be thinking, well, why can't I just flip both of them upside down? Well, in essence, it's actually cross-multiplying and then dividing by the pieces you don't have left over. So if I flip both of them at the same time, so think about what you know. Let's just use a simple fraction to show it, right? So if I had 1/2 is equal to 2/4. Agreed? Yeah. And if I flip them, 2 over 1 is equal to 4 over 2. Also still true? Yeah. So that's what's happening as I do this with this other one that doesn't have all the values in there. So if I flip everything upside down, I have R, R1, R3 over R1, R3 minus R, R3 minus R, R1. And it equals the R2 over 1, or simply R2. Okay? So I wrote it R2 over 1. You don't really need the over 1 part. It's just equal to R2. Again, it's not the only way to do the problem. There's lots of other possibilities and operations in different orders that would work, but it's a fairly decent one to do it with. So the rest of what we're going to do in section 1.2 is actually taking word problems and solving them. I think this is probably one of the most difficult sections in chapter 1 because word problems always make us get a little bit anxious, which is very interesting because a lot of times students want to say things like, when am I going to use this in real life? And then I present you a word problem and you're like, oh, but I don't want to do that. Well, that's the point, right? This is the real life stuff of using equations. Now, I realize you're not going to use every single one of these equations in real life, but I have had students come before and have dilemmas in how do they prorate rent when somebody has a bigger bedroom? How do you decide what to do if you're sharing the bathroom and your roommate has their own bathroom? And you can do that with algebra, all right? So there are applications of this all over the place, and these are a few of the ones that we're going to take a look at. So this is a problem-solving strategy, kind of a listing method. We're not going to list out every step. This is step 1, we're doing this. This is step 2, we're doing this, and so forth. But it gives you a good idea if you're stuck, what you can do in order to make some progress. So when you're taking a look at a problem, the first thing, of course, is to read and to figure out what's going on, is to understand what the question is asking. Sometimes drawing a diagram is helpful. Sometimes it's not. Deciding on what variables you want to use. Do you always want to use X? That's fine. Are there variables that sort of feel natural, like using L for length, things like that? And writing those unknown quantities in terms of the variable. So what does that mean? Well, it means actually writing down L equals length. You know, something like that to keep a reference point, especially if you like using X all the time. What is X in this problem? X is the number of adult tickets sold or something like that. Okay, so writing down what your variables actually mean. Step 4 is the part that starts to actually look like the algebra component. It's actually writing an equation using those variables. And step 5 is the solving of the equation, the stuff that we were working on in section 1.1. 6 and 7 are the parts that people tend to be like, oh, I'm just going to keep moving because I got an answer and now I'm done. But 6 and 7 are very important, and they're checking to make sure things actually work. So you're checking to make sure it makes reasonable sense. Does it make sense? I mean, we're 2.34 babies born. I don't think so. Doesn't make sense, right? Did I get negative, termites in my house? No, there's no negative termites. So you have to make sure that the problem actually makes sense for what you have going on. There's often money problems that, if it worked the way that the errors show that it might work in algebra, it would be amazing. We would double our money every 34 days in the bank or something like that. No, it doesn't work that way. You guys have had enough financial exposure to know that you put the money in the bank and it grows really, really slow, right? You borrow from money from the bank and you have to pay back a whole lot more than you borrowed. That kind of stuff works that way. So you have to make sure that what you're getting actually is reasonable for the context of the problem. But these are the 2 steps here at the end that are often the ones people forget to do. And then they're like, I don't know what it's wrong. Well, because you didn't actually check for reasonableness. So we're going to take an example. This is a money one to start with. It says that you're going to borrow some money. So you borrow $100 and you pay back $105 at the end of the month. What was the simple annual interest rate? Okay, so that's why you have a list on the previous page of some of the basic formulas we're going to be using. So what is the interest formula that you see, the simple interest formula that you see on the first page? What's it say? Good. It's I equals PRT. And I had you write this down, what each of these letters represented earlier in your notes, right? What was I? It's the interest. Okay, so the interest is not the money that you pay back. It's the extra money you pay back. Are you with me? If I borrow $100, I definitely have to pay the $100 back. But any extra that I pay on top of it, that's the interest. So what's the interest in this problem? It's 5. That's the extra amount that I have to pay back for the luxury of having had the loan. P is the principal. It's the amount that I borrowed or the amount that I invested. So what is the principal in this problem? That's the 100, right? R is an interest rate. What is that in this problem? That's what we're solving for, exactly. That's exactly what we don't know. And T is time, and how did I tell you that time was always calculated? In years, when we're working with interest rates, right? In years. This says that I paid it back in a month, though. So what do I do about that if I'm supposed to be having my value in years, and I'm told that I'm doing this in 1 month? Yeah, exactly. It's 1/12. A month is 1/12 of a year. Okay, does that make sense? Do you see where all the pieces came from? Because if you choose to put 105 in for the I, things are not going to turn out very good. Right? You're going to get an incorrect answer. It's not going to make sense. So you have to make sure that the pieces are going in the way that makes sense for the problem. So let's take a look then. How am I going to solve for R? We worked on the last 3 problems in manipulating things with variables, with letters everywhere. How am I going to do that with these numbers? A couple different options. What's that? Close, not subtract. Divide. So why is it divide and subtract instead of subtract? Right, because it's multiplied. It's a common mistake, so that's good. Yeah, we're going to divide by the 100. All right, so we can divide by the 100. So that eliminated my 100 here. Now I still have the R, and I still have the 1/12. And what does your calculator tell you 5 divided by 100 is? Or if you can just do it in your head, that's fine too. Yeah, it's 0.05. But I would encourage you to go and grab your calculators out. Not all of them are going to be so nice and pretty. Now what? Yeah, I need to multiply it by 12. So multiplying by 12 will eliminate the 1/12 because those are inverse operations. So my r is left on the right. And what is 12? I'm going to put in parentheses because it looks funny with those double dots. 12 times 0.05. What'd you get? 0.06. So 0.6? Like that? Okay, so 0.6. Yes? Okay. Now let's go back to the question and what it was asking. The question says, what's the interest rate? Now, it's absolutely true that R is 0.6. You guys did that correctly, but you haven't answered the question yet. It's asking what the rate is. Okay, so it's in percentages first, right? Everybody good with what I'm trying to get you to do? You have to think about turning the problem around to what the question asks. It's asking what the percentage is. So how do we change a number to a percent? What do I multiply by? Do you remember? 100. I have to multiply by 100. So it actually isn't 6%. It's actually 60%. And that may feel like, well, that's a lot. And it does feel like it's a lot because it's an annual interest rate that you're finding, right? Annually. So if you actually paid back $5 a month for a whole year kind of thing, that's what it's calculating. It's calculating the annual rate, not the monthly rate. Monthly, you're like $5, no big deal. I'm happy to pay $5 to borrow 100. I'm okay with that, right? But if you paid over the course of the year $60 for the luxury of borrowing 100, would you be okay with that? Probably not. You probably would not choose to borrow the $100 if you knew you had to pay back 160 in a course of a year. So the rate is always finding an annual rate. So that's why that ends up looking and feeling a little bit funny. 60 sounds like a lot. Any questions on that one? Okay. Number 2 talks about temperature. It says the temperature at 11 p.m. on New Year's Eve in Times Square is 23 degrees Fahrenheit. What is the temperature in degrees Celsius? So there's an equation that we have that converts between the two. Somebody tell me, it starts out C equals, what's next? Right. 5/9, F minus 32. Okay, so you'll notice, since we're using equations where we've already defined what the variables are, I don't need to write down C equals Celsius, F equals Fahrenheit. Those are given to you in the equations you started with. So we haven't had to do any of that just yet. But all the pieces right here are things that I can find or are given to me in my problem. So where does the 23 go? In the Fahrenheit, because that's a Fahrenheit temperature. So I've got 5/9, and I have 23 minus 32. Okay, so order of operations says, what do I do first here? What's in the parentheses? So what is 23 minus 32? It's actually -9, right? So I have 5/9 times -9. Feel free to use calculator if you want, but this one actually cancels really nicely, but don't always. So this 9 and this 9, they will cancel. So what is my Celsius temperature? Yeah, -5 degrees Celsius. Now, I've done it on both problems, but I haven't really drawn attention to it. At the end of each problem, that doesn't show up at all. This one had a percent rate, it has a percentage sign. This one has a degree Celsius sign, right? So your answers need to have units. If you're working with problems that have context, your answer needs to have context as well. So degrees Celsius on this particular problem, the percent on the previous problem. Okay. All right, so far? Okay, I think 3 is a little bit more involved, or maybe a lot more involved. Let's take a look. Julia's soybean field is 3 meters longer than it is wide. To increase her production, she plans to increase the length and the width, both by 2 meters. If the new field is 46 square meters larger than the old field, what are the dimensions of the old field? This is a really involved problem, actually. It's not just like, here's the length, here's the width, find the area. I mean, there's definitely length and width and area involved in this problem, but it's not that straightforward. The last two problems have been pretty straightforward, especially the Fahrenheit one, right? And you just plugged in the 23 and we were good to go. So what do you think you might do as you start this problem? What might be helpful? Maybe circling what's important. I think that's a good idea. So we have an original field, right? It's 3 meters longer than it is wide. I'd say that's probably important, right? And that she's going to increase both length and width by 2 meters. Also important. And then that the new field is 46 square meters. Right? Those are the pieces that are actually important to being able to start the problem. And then the question is actually at the end, it's talking about the dimensions of the original or the old field. Well, what did you do next, maybe? Okay, we might need to use an equation, right? What do you know what the equation is that we might want to use here? A general equation, what is it? Oh, somebody said something. It's not perimeter. It's a good question. Is it perimeter? Is it area? This is area because it's measuring the space inside. And it's also area. Another way you can know is because it actually talks about the square right here. So square units is always referencing area as opposed to perimeter. Perimeter is measuring length. Okay, so we need the area equation. So the area is equal to length times width. That will be the equation that we end up using. What else would we want to do maybe? You don't have to, but you might want to draw a picture. I mean, this has a really nice visual that's going along with it. So if I were looking at this problem, I am a super visual person. I see things so much better when I draw them, even though I definitely don't draw very well. So this is the original field, okay? It's not going to be drawn to, specifications here. And then here's my bigger field that's going to be 2 meters wider on either 2 meters extra on each side. Can't talk very good. Okay, so over here in this equation, L is length, right? And W is width. So generally on a picture, we make the length the longer one. You don't have to, but so this would be W and this would be L on the original diagram. But there's a piece of information that I boxed in at the very beginning that's really important right now to helping me not have an L and a W. You see what it is? It's in the box, actually. Somebody say it really loud. You guys are all saying it. Somebody say it for me. Yeah, the length is 3 meters longer than it is wide. So the L that I have in my problem right here, I don't really need the L. I'd rather have what L actually represents here, which is W plus 3. Right? It says it's 3 meters longer than it is wide. So my original field, let me actually write that one down first. My original field would have an area that's the length is W plus 3 times the width, it's W. Does that make sense? That's my original field. Now I don't know the W, so I can't keep going from there, but that's my original field. But Julia is actually wanting to make her field bigger, right? So if she's going to make it bigger, it says she's making it bigger in 2 feet in each direction, yes? Or 2 meters in each direction, excuse me. So the new width over here is not just W, what is it? W plus 2. And the new length is not W plus 3, it's W plus 5, right? Because it's 2 meters different in each direction, adding 2 to each of them. If you feel like taking a look at this is my new field. My new field would be W plus 5 on the length and W plus 2 on the width. That's my new area versus my old area. And it actually tells you that the new field is 46 meters squared larger than the old field, right? So these areas have some sort of relationship. One of them's bigger than the other one, right? I mean, obviously. So I hope I have a space over here. I do. So my new field, or my new area, minus 46 would equal the old area. Does that make sense? It says it's 46 meters bigger. Or if you prefer, you could write down, don't have to write down both of these, you could say that the new area is equal to the old area plus 46, if it makes more sense to you to think of it that way, because I've increased the size of my field, right? This new pieces here are actually 46 square meters more than I previously had. So in either direction, whichever one of these you use, I'll use the first one since that's one you probably wrote down to begin with. So my new area was W plus 5 times W plus 3 minus the 46 then is equal to the old area, that's W plus 2, not 3. The old area, which is W plus 3 times W. It's a comparison of the new field and the old field. And then we're going to distribute and multiply this out like we did back in chapter P. So if I distribute or FOIL this out, I've got W squared. My inner terms is 5W. My outer terms is 2W, so that's 7W. And then 2 times 5 is 10, minus my 46. And then on the right-hand side, I have W squared plus 3W. What can I do? What can I combine? Yep, the positive 10 and the negative 46, so that's negative 36. Awesome. Okay, let me actually do the W squared first because it's actually super friendly. If I try to move the W squared by subtracting it, what do you notice is going to happen? It actually cancels out. And that's going to happen every single time in this chapter because I'm not supposed to be working with quadratic equations. I'm eventually going to have a linear equation when I'm done. All of chapter 1 is linear equations. So anytime I have a quadratic show up, it's going to cancel itself out somehow. That's going to happen. So all I'm left with now is the negative 7W. No, it's negative, sorry. My pieces got messed up. It's W, positive. So positive 7W. Negative 36, and then 3W. Okay, so what would you like to move next? Which piece? 7W. So how would we move it? What operation? Subtraction. So minus 7W. So I have negative 36 on the left. 3W minus 7W is negative 4W. What would I do next? Yeah, I'll divide by negative 4. So W is going to be left, and then what's negative 36 divided by negative 4? 9, yeah. 9, you're thinking divide by 3. It's 9. We have to make sure we answer the question that was asked, because it didn't ask me for the width, actually. What did it ask me for? The dimensions of the original field. Well, one of the dimensions was 9. The other one would be, what? 9 plus 3, which would be 12. So I actually have a field that is a 9 by 12 field, but what are the units on this? Close, just meters. So we're measuring the length, and length is always in linear units, so it's just meters. We could be asked what's the area of that field, right? That's another question that could have been asked. What's the area of the original field? And what would I do if I was asked that question? I'd have to multiply the 9 and the 12, right? That's how I would find the area of the original field. So I'm going to cut that just a second because it looks funny. I'm going to write the word by in between. You can put an X between there, but yeah, it's 9 meters by 12 meters on that field. All right, so here's what I'm going to do. I'm going to pause right here. We will pick up with question number 4 next time. We have 3 more questions in this section. I have tests to hand back, and I want to chat a little bit about that before you leave. And so this is probably set inside of my math lab to be due on Wednesday. It'll be pushed to Friday, obviously, so I'll get that fixed when I get down to my office. And we'll pick up here on Friday or on Wednesday.